On stage is our next speaker, Pablo Ribalta, who works at NVIDIA, delivering solutions to healthcare applications and improving models used in the industry. This is AI in Healthcare, presented by Pablo Ribalta.
Thank you. This is Virginia Apgar. She was an American anesthesiologist who, in 1952, came up with the idea of the Apgar score, who some of you might have heard about. So the Apgar test, or the Apgar score, is it's a score that is assigned to a newborn after birth. It ranges from 0 to 10, and it's calculated on the basis of 5 main features that the baby displays, which are the appearance, the pulse, how it moves, how it reacts, etc. So each one of these 5 features is rated from 0 to 2. And the result is the aggregate score of all these features. At its heart, the Apgar score is an algorithm. And even though we might not think about it this way, algorithms are present in medicine. In fact, algorithms are present in our world in many different things. We live in a world where we can send people to the moon, where we have telephones that talk to us, where we have radio stations that play only the music that we like. However, some disciplines, like medicine, still remain like an art, only at the reach of very few of us. So, at the end of the day, physicians take complicated decisions based on the data they see, what are their observations, and these are algorithms too. So today I will be talking about how the most cutting-edge algorithms nowadays, which is AI, deep learning, are being applied in the field of medicine. And it has become one of the most challenging and frontier topics, let's say, on modern computer science. So the story comes, from way back. When it appeared, artificial intelligence, it was a long time ago. Artificial intelligence, the goal is to deliver on this promise of building machines that are intelligent, like replicating some type of intelligence similar to human intelligence in machines. This, created a lot of expectation and a lot of excitement, and the first success on this part might be when Arthur Samuels in 1957 came up with a program that was able to play checkers. Now, what Arthur Samuels realized is that he wanted to play checkers with his machine. But, for all of us who write code, if we have to specify the logic of even a simple game like checkers in code, this requires a painful and excruciating level of detail. There are many bugs that can appear. And, if we think about more complex problems like the game of Go, writing that into code without making any mistakes is very complicated. So it actually worked for him. His program ended up being a state champion of, I think, Connecticut. And this was 1957, so there were already some successes and some excitement around artificial intelligence back then. Later on, around the 80s, a new subdiscipline, let's say, appeared, which is machine learning. Machine learning is a subset of artificial intelligence. What we want is to have machines that can perform one task in an intelligent way, or then can take decisions based on data. So the scope is not as broad as artificial intelligence, but machine learning is, delivering good solutions. A good example might be, for example, the spam filter that is used in email clients. So depending on the email client that you have, you will see that your emails are sorted in spam, it's sent to the bucket of spam, or it ends up in updates or social or whatever. So this is machine learning. The algorithm learns from the data it gathers. And last but not least, you see it correctly, there is deep learning, which appeared recently in the 2010s. And it was, a series of breakthroughs that took machine learning to a next level. So what we see here is deep learning is a subset of machine learning. The appearance was triggered by ImageNet. For those who don't know what is ImageNet, it's a data set with several millions of images. And it's kind of like the Olympic Games of computer vision. So every year, many researchers participate worldwide and try to beat the previous results. And for many, many years, classic machine learning algorithms did well in this task. But in 2012, something changed. The first deep learning solution was presented to ImageNet, and it smoked all the other algorithms. And this was pretty big at the time. From that point, we have grown a lot, and things have gotten only better. So, you know, how does deep learning work? What is the science behind that? What makes it different? Actually, deep learning is exactly the same thing that we had in the 80s. But what happened with traditional algorithms was that, you know, as the scale of the problem was growing, the results were not scaling in the same way. You know, it eventually plateaued. The computational cost of training everything was just, you know, prohibitive. And it was just simply not scale. 2010, something happened. GPU was applied to machine learning, and we got deep learning. And from then on, we have gotten unprecedented results in many tasks, like image recognition, speech, text understanding. And a lot of these early advances have been applied to many different fields. One of them is medicine. So looking in perspective to this, you know, what was the driver of the change? So it was first GPU acceleration. And then something else happened, which is worth of notice. The previous approach of machine learning was that we would have an expert that would select the features that we wanted to learn from or that we wanted to classify from. And the algorithm would decide how to classify them. Now, let's imagine I want to say if this picture is a picture of a cat or not. So if I'm an expert in cats, I might say, well, a cat has 2 ears, 2 eyes, and mustache. OK, fine. But if I show it a photo of Salvador Dali, for example, it might tell me that this is also a cat because it fulfills all these features. So if we try to classify complicated things, then it becomes not very trivial. In medicine, for example, doctors often struggle, even though they are capable of identifying stuff, they often struggle to tell us what features they are looking for. So in deep learning, what happened is that since we had more compute, we were able to make our networks deeper. And the first layers were able to act as feature extractors. We'll see more about that later. We also have better math. Some improvements were made along the way, because the problem we had earlier in the 80s or with this traditional machine learning and traditional neural networks is that we could not build models that were very deep, because it would eventually stop learning, because we would not be able to update everything. Some updates would be lost towards the end. Now math is more robust, and we can account for those cases. The differences are there. We get superhuman accuracy. We are able to improve results of human beings in different tasks, for example, image recognition. But these new systems are super power hungry and compute hungry. And the last difference is the scale. The scale now is just massive. It's it continues growing and growing. And before we had data sets that were like 30 samples, something like that. And nowadays these are, or MNIST data set was considered state of the art, and nowadays this is just a toy problem. We are talking about data sets with millions and millions of images, of terabytes and terabytes. It's just, it's incredibly large. So ultimately these systems came with a benefit. And well, here I will explain you a little bit what we have here. Here's a comparison of the work breakdown between classical machine learning algorithms and deep neural networks. Okay, I don't see the colors so clearly here. So, the first part for, classical machine learning algorithms, data preparation was a significant chunk of the process. Nowadays, it still is, even more so, especially for medical, because some images require a lot of normalization. But the main difference that we see is that the feature engineering in classical machine learning just took most of our time. We were all the time trying to select the best features, trying to do feature dimensionality reduction, these type of things. Deep neural networks are just, they learn what is important from the data. And that's very cool. That's very cool. We'll see later how this translates into medicine. This means that for modern algorithms, such as deep neural networks, we can spend much more time in optimization and much more time in model design. So actually the process from research to rollout is much more streamlined, and we can really spend time in innovation and spend our resources innovating, basically improving our results, or the result of our model. So actually, what is about this deep learning? I mean, what does this actually happen? Let's imagine that we want to, classify a picture. We want to know who is this person. And the way our deep network would work, for image recognition, would be that we would have some layers that act as feature extractors in green, and then we would have a classifier on top, like the traditional machine learning solution on top of that. And everything is trained together. In the beginning, the first layer, computes some type of activations. And these activations represent the lower, let's say, like the most basic filters that we are going to have. For those who have background in digital signal processing, you know that if you have a signal and you apply a filter, then you can obtain different or highlight different properties of the signal. So here this first layer, let's say, learns some filters that act as edge detectors and things like that. As we get deeper in the network, features become more complex. So they are starting to get aggregated, and the complexity of the features grows. And we start seeing different parts of the face, like we see an eye, we see a nose, etc. And later on, as we travel a bit deeper into our network, we already have a very semantically charged features that combined, help us, let's say, identify the whole face. And once we classify it, we see that this person is Virginia Apgar. So that's actually the way it works. The revolutionary part is that all the green layers that we see here, these are the feature extractors, and this is what the network is learning automatically. On top of that, we have the regular classifier. The life cycle of this type of model is very simple. We start by a network that is typically untrained. So we just simply have it connected in some way that we decide that this is going to be the success. And we train it. So we have a training set full of samples. For example, we want to say this is going to be cancer or not. So we run it through our data set, and we basically feed it all these examples and try to make it as accurate as possible. At the end, what we have is a trained model which has already a new capability and can be deployed anywhere. And for that, we use inference. So we feed it new data. And it's able to tell us that, OK, the image that we are getting there, this is going to be cancer. So this is actually performing classification. Is it cancer or not? We are training here for this purpose. So that's actually quite simple and straightforward, but this has many advantages. And is that when you have one model trained, you can deploy it anywhere. It doesn't matter if you are, for example, in Poland, or if you are in a remote location. You can take your model that is very well trained, deploy it in any device, and you can actually make a difference. So how does this magic actually happen? How does the training actually take place? From a very simplified point of view, a neural network is a set of weights that get aggregated to compute a score. This is basically a similar process as the Apgar score, somehow. We have some set of observations. We have some weights that assign the importance to each one of them. And this is the product of all the input and the activations are computed, and this generates an output. So let's imagine that we have some input features that are fed into our network. So then the result is computed. And what we have here is the output of our network. So basically, this might be, let's say, is this cancer or not? Or is this, what is the score, Apgar score that we want to calculate, or something along those lines. Then we compare it against something that we know, because in all training data, we have samples, and we have their diagnostic. Because what we want to teach the network is that, OK, you have this image, but you should predict this, actually. So you compare the outcome of your model with what it was supposed to be predicted, And what it gives you is a loss. Let's say like the distance, how far away you are from your ideal prediction. So you know how much you have to improve. This is fed to a component, it's called optimizer, and this guy will tune your weights, and this happens again and again and again for each of every examples. Imagine if you have a data set of millions of images, this happens millions of times every epoch, let's say every time you go through the data. The type of update that you make, how big is the adjustment is regulated by a parameter, it's called step size, that is fed to the optimizer, but that is basically what's going on all the time. You have this cycle of reinforcement and reinforcement and reinforcement and tuning and tuning and tuning until the weights are as good as you can possibly get them. So now that we get that out of the way, now that we have a little bit of an idea of how this thing is going to work or how these models basically behave, we can take a look at the landscape of AI in medicine. So in medicine, we have many different use cases. I have here some examples. Something that it really shocked me lately is that we can detect growth problems in children by examining the bones of their hand. So actually what we are doing is that we have a data set of images of X-rays from hands of children, and then we have some data about how these children develops in the future. So if we can train an algorithm on this data, what we will see afterwards is that when a new patient comes in, we can take an X-ray of his hand, and then we can see how is it going to work out in his or her development. Also, AI can be used to predict and prevent disease. Another of these interesting use cases is that I saw lately a paper about an algorithm that it is able to predict a seizure with 99 point very high accuracy 1 hour before this actually happens. So that is pretty huge. How is this done? So we can have biometric data from a patient, and we can attach a label that will tell us if this patient had a stroke or not. So we can train on that, and then we can use it live. So we can implement that in a device or something like that. Also, insights for effective medical decision making. So we can, collect history information from the patient and say, well, what therapies are going to be better for this patient. If we are able, for example, to analyze the genome of a patient, we can have dedicated therapies that can help. This is a big breakthrough in cancer. And well, all these things that I'm telling you is things that are being done right now. Also for cancer diagnostic of MRI images, so we can, let's say here down on the left, we can feed MRI scans, we can have a ground truth provided by some radiologist that can tell us, where the tumor was. We can train networks for that. We have also, can help doctors in the surgery room. We'll see more about this in a sec. And at the end, yeah, we can create personalized therapies. So you see, the landscape is very big. It's very hard for me in this conference or in this presentation to cover every single detail. So I will try to give you an overview of what are some problems, what are the approaches. But the scope of this is very, very vast. So there are many different use cases, appearing new ones every day in many institutions around the world. So actually, what is it possible to do with deep learning in medicine? So the influence that we can have is actually pretty big, because in cases of imaging, these type of systems get on par with specialists. This is complicated to measure also, because two radiologists can give you different diagnoses, but in general, we are up there. These systems do very well. For example, in pathology, a lot of mistakes, let's say, are performed in the diagnosis stage. So we can really help doctors with this type of classifiers to improve their diagnostic. And we can help in the clinical decisions, because it will allow us to also, using these systems, get in these conditions early before they manifest. For example, in the case of breast cancer, a very high success rate is achieved when you catch it early. So if we are able to provide these strong classifiers that can tell us, okay, this thing looks strange, this thing probably is breast cancer, so this is also important. So let's say in general there are these three main areas of focus. Methods that improve the diagnostic. Whoops, okay. This should be detection. So methods that improve detection, and then methods that focus on generation. We will see about them in a sec. So the first one I'm going to talk about is the use of deep learning in pathology. So the idea is that whenever you are to get a diagnosis from a doctor, he has to sit, he has to check, but sometimes images are very complex, and sometimes the diagnostics are suboptimal, let's say. So the idea is, how can we bind deep learning or machine learning or this type of methods with a physician and improve the quality of the diagnostics? So this is part of a subdomain called digital pathology. So typically the way it works is that, let's say you want to have a biopsy, right? And they want to take a piece of tissue from your body. This tissue then is taken to a laboratory and is cut into very, very thin slices. These slices then are passed through a machine that puts them in some type of wax. And these very, very thin slices then are later analyzed by people in the laboratory. And they are looking for certain, let's say, structures in the tissue. You have many, many of these samples, and they are very big. The process of, generating these samples and keeping them safe is quite costly. And the field of digital pathology, what it aims is to use computational devices to solve that. So, this is one of these images that we see here. This image is around 40,000 pixels by 20-something thousand pixels. You can really get very, very, very close in this image. Think about a doctor that has to say, let's say, this is a slide, because this is called whole slide imaging. So you are looking at this whole slide, and you have to say if this biopsy, for example, you suspect that this patient has cancer, so how or what is the grade of this cancer? You have to look at an incredible amount of data. Here we don't see it, but this image, in real size projected here, it could, arrive to the street and it would just be incredibly huge. So the doctors have to sweep through all these images, trying to find all the areas of the tissue that are, let's say, potentially hazardous for the patient. And now they can do it with computer devices, and this has become a very important thing because it's very promising, it's faster, and it's much cheaper. Here what we are going to try to look for is to certain structures that will give us some hint of how, of what is the stage. We'll see it in a sec. But some open challenges still remain. The technology is still a bit limiting because laboratories, for example, don't have supercomputers or GPUs, all of them. And currently, this is a very low throughput task because it takes the doctor a long time to go through each one of these slides. So let's say that if we wanted to attack this with deep learning, we would have to look at these 4 different classes or try to see, these are patches from that big image. So what we see here is a gradation of the tissue. So different regions of the tissue have different properties. So on the left we have normal. This is how normal tissue looks like. So in the previous slide we said that in blue we had the nuclei of the cells. In pink we have the cytoplasm. So actually these samples are stained. They add some coloring, so you will see them better under the microscope. Here we have a benign use case. This thing is not normal. This thing is not normal, but it's not bad. But here things are starting to look not very good. This is carcinoma. This is what you don't want to have. However, carcinoma here is contained. We can still see the boundaries of the cells, so or some structures here. So it's not that bad. But here we have invasive carcinoma. Everything is all over the place. Everything has spilled out, and this is very bad. imagine that invasive carcinoma appears only in one small place in the slice that you were looking at before. This, missing this is what you really don't want to have. So actually, how do we attack this type of thing in deep learning? So the first approach I'm going to show you a little bit is how these classification tasks are attacked by deep learning. So this is what is called a convolutional neural network. In particular, this one is called VGG16. It was released a few years ago, so it's not state-of-the-art model, but it will do very well for this task. It's rather small, but it will be very effective. And it's based on two main operations, convolutions and pooling. So convolutions, you have them here in green. Pooling, you have them in light green. The way it works, basically, is that the first layer, as we saw, will, in green, this first convolution, will extract information about the edges of the cells, try to tell us, how the structure looks like. And this pooling operation, what it does is that it reduces the input size, because not all the information, all the features that you are highlighting are going to be important. So from the activation, it's throwing away, let's say, roughly half of the data. Let's say the half that is the least intense. This happens again. We have a couple of convolutions more. We throw away the least important or the least, catchy of the activations we are producing. This happens several times. And here is finally the classifier. Now, if we think about it, we can apply this network as a sliding window over the whole slice image. And even though this is 40,000 by 20-something thousand pixels, by breaking down into patches, we can actually take care of that. We can do it at probably maximum accuracy all the time. The doctor, when he starts, he's fine, but then he gets a little bit tired, has a coffee, goes back later, and he starts maybe getting a little bit less accurate. But this thing will perform all the time with full accuracy. Modern approaches, of course, are a little bit more developed than that, so that there might be bigger or they might present a different topology. But they include the presence of residual connections. Residual connections is when this last convolution, for example, will be connected to this one here. This will be done so when we have the adjustment of the weights in the backward path, as we've seen before, it will help the gradients flow back here, so it will present a more solid learning. And the modern attempts also attempt to process the whole WSI image. But here is challenging because this is an engineering challenge to feed that much into memory. How can you do that? You can load it in parts or things like that. So this is an open area of research. So if someone wants to tackle that, I can tell you where to send pull requests. So, normally classifying models look like that. This is a convolutional neural network, and you can use that for this type of task. If you want to set up a challenge for yourself, there is a dataset called Patch Chameleon, which is based on the Chameleon dataset with 327,000 patches that you can classify. It is actually, building up to some type of competition type of thing. So you have the sources here for the dataset. You can download it from GitHub. And here there is a Kaggle competition that runs all the time. Another approach that we saw before, it's not only diagnosis, it's also detection. So detection aims at helping radiologists identify structures that should not be there in the first place. So let's say when you go into let's say into some magnetic resonance or into some tomography, an image is produced. So there is someone has to calibrate the machine, someone has to make sure that data is collected properly, and this is stored in the hospital. Then the radiologist looks at that and tries to identify suspicious structures in your body. So the body at your point looks like a 3D volume, and the doctor has to sit down and spend a little bit of time on that. So he has a collection of slices that basically when we go through that, it looks like this. So this is a head going from bottom to the top. And this process of identifying these strange structures might take a while to the doctor, because an MRI has different modalities. So when you have an MRI, actually they are taking, you know, several sequences from your body, and each sequence highlights something different. Some sequences focus on the blood flow, some sequences focus on the tissue itself. So it's a lot of information that needs to be aggregated. Radiologists can spend like a couple of hours looking at your scan. And the most interesting thing is that the doctor doesn't need to look at all the data. Well, he only needs to look at the slides that have a lesion. So most of his time, he is looking at slices where basically there is nothing. So there's a lot of room for improvement there. You know, this is a very, very active area of research right now, because as we saw with digital pathology, medical imaging is undergoing a boost, you know, a whole revolution in different imaging techniques. Now we have, I don't know, with laser, with PET-CT, MRI, many, many different type of modalities. And it's becoming, you know, more and more accessible to get these things. So there's actually a lot of data. Unlike in other domains of deep learning, for example, the arms race in medical imaging is not about publishing more and more accurate models, it's about handling more and more diverse data. So this means that the effort in normalizing the data is big, and you know, the data availability is not a problem. So the key models that do well in this task are what is called U-shaped models. We'll see them in a second. You might, you know, some while ago, they used to be called autoencoders. I don't know if you have come across this word, but now they do a little bit more than that, but we'll see this right afterwards. And they rely on the skip connections that I have explained a little bit before. So let's imagine on the left, we have a slice that it clearly has something wrong. This is a T1 slice, so it focuses on some properties of the tissue. And what we see is that down on the right, this individual has a foreign thing. It has an abnormal structure that we want to segment and we want to take out. So the way we will train it is that we will feed some images of this kind, well, probably without this border, just the binary mask. And we will tell him, from this image, I would like you to predict me only this thing. Okay, I want you to generate me a new image that will be all black, but everything will be zeros background, but the ones will be in the area of interest. So what this network actually does, if we think about it in the context of what we've seen so far, it doesn't have any classifier. It doesn't have any classifier block. It's just convolutions, pooling, and just an activation at the end. So actually, this network is not going to produce only a single label classification. It's going to do it per pixel. What we have here in gray are these skip connections that I was talking about. So we start with a convolution that extracts the features that most basic, let's say some edges and things like that. And then we have the pooling. So we discard the half that is the least intense or the least important. We have a couple of convolutions more, we discard. We have a few convolutions more, we discard. And we arrive here at this bottleneck. And here is very interesting what happens. Because if you've been paying attention, you will see that here the image, let's say, was 100 by 100 pixels. But we are performing 1, 2, and 3 downsamplings. Here the image is very compressed. We have a very compressed representation of the image that has only the required information for its reconstruction that is performed in this part. Convolutions are aggregated, and they are used to generate an image at the very end. It's very hard for me to go into detail about these models, but think about it this way. If instead of training it to predict this binary mask on the right, you would train it to predict the same image, so to perfectly restore this image, you would eventually happen to have here a very, very compressed representation of the image. Initially, this image is 100 by 100. Maybe here it would be like, I don't know, 50, 25, I don't know, 12 by 12. And this 12 by 12 image has enough information to recreate the original. So these type of models can also be applied into many, many different domains. They just happen to be very good at generating images from compressed data. So, for example, compression of files, compression of sound, things like that, they can be used perfectly. So these models are very powerful. They work in 2D, they work in 3D, and for 3D, they are very computationally hungry, but the results really are stunning. They can be done for many different structures, they can do for many different organs, and they are simple, but they are very powerful. The challenge, though, is not about building a model that will do very well segmenting brains. You know, this is a very pragmatic approach. Some people, you know, focus on that, that's fine. The thing is not only about an organ. The challenge of these models is tackling multiple organs. And why is that? Brain has a particular set of features, but different organs, like for example the pancreas, are very different, behave very different. The pancreas is like a jelly that is resting between some other organs, so it's very difficult to say where it ends and where it starts. So models that do typically well in one organ, they don't do very well in other organs. So the challenge is to achieve something that will work, you know, across different domains, and this is what this challenge is for. So we have this medical segmentation decathlon. These are 10 different data sets. So I'm throwing you these challenges in case you want to explore it yourself after the presentation or something like that. But here what we have is like 10 different organs. So we have liver, we have brain, we have spleen, we have lungs, we have many, many different organs. I think pancreas, is pancreas there? I don't know. But the challenge is to do as good as possible in all of them with the same algorithm. This is really one of the challenges. Yeah, data is in different modalities, and if you want to fetch the data, you can get it here. The challenge is here is already finished, but the leaderboard is still active because, you know, this is a substantial effort by the medical community to deliver these models there. So yeah, very challenging area too. Then we have the last part I'm going to talk about is generating models. They are used in medicine, but a little bit tangentially. I wanted to talk about them because they are very interesting, and they always kind of like spark ideas in people. Let's say, a way to understand them is that you can have, instead of one model, you can have two models. One will be generating stuff, and the other one will have a goal, which is to detect if something is real or is fake. So the goal is that after some training together, you will have a system that will be able to produce artificial data and will be as credible as possible. A good example would be of this type of problems. If you have someone or a person is falsifying banknotes, let's say with fake money, you have the bank. The bank has a system to detect this fake money. So in the beginning, some of these fake notes will kind of like be around, but the bank will eventually be able to catch up and catch them. But the falsifiers then have to get better to fool the bank. And this happens and happens and happens until the bank is very good and the falsifiers are both very good. So here is a similar type of thing. We can attack many different types of data this way. First, for example, we have here complex molecular structures. DNA is a molecule. The whole chain of DNA is around 2 meters long. I mean, I'm not expert in medicine, so I might say some inaccuracies, but anyway, you get the idea. It's like 2 meters long, and it is folded in a particular way where it takes very, very, very little space. Now, in the beginning, people like to think that the folding of the DNA was random, but it actually seems to be that it's not random. The thing is that there's so many genes and so many stuff that you have to sequence that it's very hard for, you know, even molecular dynamics to generate these complex structures. So in the case of proteins, which is a simplified example, it is possible to have deep learning models that will predict the final shape of a protein based on the sequence. In the cases of USG, it is possible to take an image in USG and render the 3D volume. So let's say if you have a baby in your belly and you can see it in 3D, so you can see the face and everything. It looks a little bit scary, but I was looking for a good picture for this slide, but I decided not to include it. But I prefer the 2D. But you can Google it, it's cool. And here we have OCT image. This is an image of the retina. And what you see is that it's very, very noisy. Normally, these images have to be taken like 12 times or between 6 and 12 times, so you can kind of like average and remove the noise. But this has a cost. Machines have to be used more, and the investment by these clinical centers is more significant. So you can use this type of models also to remove noise. So as you see, they are very, very versatile. The way they work, as I said, is by setting up this adversarial scheme. So we have a generator I used for this purpose, like the network that we have seen before. So we basically have a network that is trying to remove the noise. And then it's producing these outputs. This output is similar to the original, which is here, but it's not the same. It's like a little bit blurred, right? And then we take it and we feed it into a classifier like the one we saw in the previous, in the first example. And this classifier will tell us if it is real or fake. So these networks are trained together by steps. So the generator will eventually learn how to produce very high quality images. The discriminator will learn how to identify fake images very well. And this will help push the generator to generate better images. So in this setting, they cooperate together to improve the quality of this image that is being generated. At the end, what we want is that we will probably discard the discriminator because we don't need it anymore. We will be left only with the generator, but this generator will be able to produce very high quality fakes that were not there in the first place. For example, here what we are doing is that we are removing the noise. So we inject the noise in the image and we try to remove it with the generator. Possibilities with these models are endless, and they always spark the curiosity and the imagination of people. So, now that we have seen 3 of the mainstream examples, what are the open challenges really for healthcare? Because, these little models are cool, but from the bird's eye, the field of healthcare has a lot of, difficult parts. One of them is to ensure data privacy. We've seen that, we can train, but we need data. And this data belongs to people. And this data, well, nowadays we have laws that prevent us from, using this data freely and sharing it freely. So how can deep learning actively try to address that from an engineering point of view, not only from the regulation point of view? At the end of the day, we need the data. Yeah, we need to find a good way to share this data, and the organizations have to ensure this privacy. But we know how things work in practice. On the other side, we want to build the best tools. Data sets are getting bigger, new modalities are appearing, new types of data are appearing, new problems are being solved, and the data has to catch up. So for this, we are also working hard. Hardware is just, has to catch up with the state of things. So on the first thing of the privacy, at NVIDIA, we are working hard on something that is called federated learning. That the aim is to try to mitigate the problem of privacy. And that's actually a very cool and very intuitive way to work. Normally, what we've seen before is that you need some data to train your model. So if several organizations are meant to cooperate by sharing data, you need to have a big silo, and everyone has to share their data. And if some agreements were in place with the institution, then people have to sign again. This is not very practical. So actually, federated learning, what it does is that instead of sharing the data, what you are going to share is the model that you are training. This is similar to the way that these predictive keyboards work in your mobile phones. So what we have here is that an institution is working with its own private data. It trains its model, fine. I mean, first of all, there is a federated server that has the target model that you want to train. Okay, the master model is sitting there in the federated server. Now, when a private institution with its own private data trains, it takes a copy of the federated the model in the federated server, and it trains on that with its own data. Then it computes an update to this model, and it sends only the update encrypted to the federated server. The federated server then decrypts the update. It does that for all the institutions that are taking part of the federated learning. So in every step, let's say each institution goes through all its data, gathers an update, encrypts it, and sends it to the federated server. Then the federated server averages all the updates and updates the master model, let's say. So then it's copied back and the training resumes. This way, each institution can use its own data without having to share it with anyone. You only share the update to the model, which is probably not going to trace back to the data. And this update is, on top of that, encrypted. So this way, there is no privacy concern with the data, and the problem of privacy can be mostly avoided. On the bottom, you have the source. This is a paper that was released recently, where you can learn more about this. But this is going to be, hopefully in the future, one of the main ways that these institutions will partner and will cooperate. Another thing is about the hardware. NVIDIA, at its heart, is a hardware company, so we are working very actively trying to make our hardware better and better. So what we've seen before is that the way neural networks work is we have an input, we have some weights, there is a multiplication, we add some bias term. I didn't include it back then because I wanted to simplify it. But a few time ago, well, a while back, when we had Pascal and now we have Volta, there will be more generations anyway, but the tensor core was introduced. The tensor core is a little piece of hardware that is able to perform a multiplication and addition in a single step in mixed precision. So we have multiplication and addition. This is the same thing as we've seen in the previous slide at the very beginning of computing the input, which would be this green matrix A, multiplied by the weights, which is our matrix V, and adding the bias, which is in the matrix C. This is performed in one step, and it gives us a very tremendous boost. Tensor cores are getting better and better, and this also, enables us to do it for FP16, because these two guys need to be in 16-bit precision. Until now, deep learning was performed mainly in float 32, because it's very accurate. At the end of the day, we have these very small updates that we want to capture. But, not everything needs to be represented in floats of 32-bit. Some things can be represented in 16 bits. So this is part of some overarching, let's say, improvement that is being performed to be able to train in lower precision. This way we can leverage tensor cores, and we can, for example, with changing only one line of code, you can train in mixed precision nowadays in TensorFlow or PyTorch, and you can get a boost of like 60%, 100% boost without you having to do anything practically. So hardware is also a big driver of this, because data sets are getting bigger, and we also need to fit them in memory, and we need to process them faster. So, we've seen a little bit what are the main approaches, what are we also trying to deal with complicated topics right now. But, at the end of the day, we are entering in some uncharted territory, because deep learning, when applied to medicine, it allows us to do things that before we didn't think it was going to be possible. A cool application I've seen is to use deep learning to monitor babies in their cribs.
Don't worry.
Yeah, okay. Yeah, good attraction. Okay, so deep learning for baby monitoring. You might say, okay, this is useful. Nowadays you have sensors that tell you if the baby is turning around or something like that, but would you be comfortable having a system that is monitoring your baby or monitoring somebody and collecting biometric data? Okay, it is possible to do it. Some people will say, let's do it. But, it opens, some ethical implications, let's say. On the other hand, we have the ability to create personalized therapies. If we use deep learning for these big problems of genome sequenciation, we can process this huge amount of data in our DNA, and for example, now, I think it was in Spain, they are able to provide you with a cancer therapy that is targeted specifically to yourself, and it has proven to give very good results. So it would open the door also to this type of thing. This would be a massive, massive improvement to the way that, for example, cancer is treated or different conditions are being treated. So, it really looks cool. It really looks cool. At the end of the day, someone will have to access to your DNA. So, I don't know. It's cool, but what about that? And also about disease prediction. I saw the same way that we can predict that a stroke is going to happen. You know, there was a paper some time back that could tell you that there was an algorithm that could tell you if in 10 years you have a chance to develop Alzheimer's disease. It sounds like a good idea, like something that you might want to do, but would you really? Would you like to have this test? Would your partner be comfortable with that? I don't know. So just because we can do that, does it mean we should do it? And now that I'm finishing, I wanted to share with you something funny. We tend to think that deep learning is so powerful, that the hardware is so incredible. But at the end of the day, we are trying to copy our brains. And our brains are an untapped source of wonder. You know, the potential is limitless. But not only the brains of humans, also the brains of birds. What I'm showing you here is that, you know, during 15 days, they trained a flock of pigeons by, how was it? They were shown some images like we saw in the beginning with this histopathology images, this in situ carcinoma and things like that. And they were putting some food in them, in those that were not healthy, let's say. So the healthy ones didn't have any food, and the ones that had some strange stuff, in situ carcinoma or whatever, they had the food there. What they found out is that the pigeons eventually would figure it out. The pigeons would eventually go only to the images that had lesions because they knew that the food was there. And you know, in 15 days, the birds were able to tell the difference. Not only that, but if we aggregated the results, I mean, they achieved, what does it say, like 85% of the time, but when they cooperated together, they seem to have gotten very close to the results that a pathologist would achieve. So what am I trying to, well, I put the link here for those of you who want to learn more about that. It's a very interesting paper. What I'm trying to tell you is that it might look like we are making very big advances, and we are. We are changing the way that therapies are constructed. The diagnosis is being performed. But we do that by imitating the way our brain works. Experiments like this tell us that, well, we have succeeded at imitating our brain, but maybe we should keep trying or imitate it a little bit more, because if a pigeon is already able to do something like that, so, you know, the threshold is just incredible. You know, a lot of challenges lay ahead of us. The only thing that we can say is that, well, there is a lot of people making effort, not only at NVIDIA, in industry, in academia, and healthcare is a very hot area for AI at the moment. There is much research going on, very interesting projects. And well, I will leave you with Dr. Pigeon for a while. And yeah, thank you very much. I will be taking questions.
So I have a question, because you didn't really talk about data annotation, and data annotation is really important, especially when we have such big data sizes, and we can really have great algorithms, but when the data annotation itself contains errors, then these errors will come into the algorithm. So my question is, what are the tools for the future? How can we increase the rate of the annotation, and how is this data annotated today?
Mm-hmm. Okay. Yeah, that's a very good question, actually. Machine learning and deep learning models are only as good as the data that you feed them with. So annotating the data is the process it's a process that we know that something, some tissue is going to be healthy or not, that the volume has a tumor. So actually, how this data is annotated, it depends actually on the type of data. If we are talking about MRIs, it's not uncommon that these annotations come from a radiologist or a group of radiologists who are annotating this data beforehand, so this is a very time-consuming effort. If we talk about pathology, these histopathological images, so it's similar in a similar way. The ways that that I guess we are trying to improve that, for example, at NVIDIA we have tools for assisted annotation. So the practitioner can kind of like select some areas that let's say you have a tumor, so he can click in the center of the tumor, and the tool will try to find an outline around that. Okay, then the doctor can kind of like adjust the boundary, but this is not that simple because the boundaries of tumors are sometimes full of blood and full of liquid, so it's very hard to say when the tumor begins and when the tumor ends. You can segment, for example, organs if you want to build an atlas of the body. So there, a tool like that might actually help you because the boundaries of some organs are clearer. But for example, organs, like I said, the pancreas, are very hard to segment. So you're right, annotation is very complicated and it takes a lot of time. It's a very broad topic because it's a lot of different initiatives and a lot of different types of data. If you have ECG, for example, cardiac data, cardiac waves, so annotating that is very, very different compared to annotating a PET-CT image. Okay, so normally what you require is to have a practitioner or to have an expert annotating this thing, and the methodology varies. There are some tools for assisted, but not for every case.
Thank you very much.
Thanks.
So one additional question. So is this tool that you guys at NVIDIA are using, is it AI driven or is it using another template? Is it using edge detection?
It has a combined approach, I guess. I'm not familiar with the specifics, but I wouldn't be surprised if besides AI there is something else under the hood. Yeah.
Oh, thank you very much.
I have a question about this federated learning, because if we have one server that only contains the model that are trained in different hospitals, how he can distinguish that this model is better than the second model from different hospital? Because those models are learned by different data, and even if we feed the model from the hospital B with the data from hospital A, it can have different accuracy. The second model. How we can distinguish which model is better?
So actually you are not copying the model back to the server. What you are copying is the update. Let's say when you go through all the data, you produce an update that is regulated by the step size, what we saw in the beginning, right? So you are calculating some delta, how much you are missing, so you will be better. So this delta then is being sent to the server, and all the deltas from all the institutions that are taking part on that are being averaged. So you get like the minimum, like the average update that would kind of like work from all the updates from everybody. So this is analogous actually as if you were using the whole data for training, as analogous as it can possibly be. So actually what you copy back is the model to the institution after it has been updated. So you are only sending the update to the server and getting back the new updated model. But you have no idea when you get it, how many institutions are taking part, what was their delta. You don't know about that.
Okay, thank you very much.
Here, I see one person.
We could see that we have one neural network and plenty of data to train those neural network. And is it possible to combine a few neural networks into one? For example, you trained a few neural networks, and you want to take a few and make one consisting of the experience of a few, like pigeons. When you took 15 pigeons, the result was better.
Yeah, so this is called ensembling. So you can actually train separate neural networks and then take a decision based on the scores of all of them. So you can have a scheme for voting or some type of thing. So yeah, you will have like all the networks that you have trained, and you will feed them the data, and few of them will tell you that, yeah, this is A, some of them will tell you that this is B. So if you have like 90% telling you that this is A, so you will be more confident that this is A, let's say.
But in the case you still use a few neural network, and I meant if it is easy to combine into one and to reduce significantly the amount of artificial cells, I would say.
Yeah, I mean, there are similar, I mean, there are probably things you can try in that regard, but I wouldn't see that really working, because I think that the benefit of having different neural networks is that they will offer you different sides of the truth, and then you combine all these different opinions and you gather your final answer. I think that what you are proposing translates more into building a very, very big neural network at the end of the day, and you know, this would maybe deliver some improvement, but I don't think it would beat, you know, having several of them with separate opinions. I don't know.
Okay, thank you.
There was somebody here who wanted to.
Who wants the mic?
Gentleman there.
In the beginning, you had a picture about backpropagation. Could you put that back?
Yeah, sure.
With a formula.
Whoops. It's a simplified backpropagation, so some details there might be missing, but you don't want to knock people out in the beginning.
Well, why not?
It's 1 hour slot, so it would be a long time. Oh, there
I think
it
it
was.
was that one.
Yeah, let me use this guy. Okay, so at what stage do you want
Next
me
step?
to?
Next one.
Mm-hmm.
Yeah, okay. Now you're going to learn. So you backpropagate the error on the right side, but then you can update either your coefficients or say the previous layer should have different outputs because your the inputs are not fixed, they are outputs from the previous layer. How do you decide between updating the factors and propagating the error back to the previous layer? Both can lead to the optimal solution.
Okay, I think that, I mean, the goal of this image is to simplify what's going to happen, but if we think about the full layer, you know, the input to the next layer is going to come from y prime, right? So then you can use the chain rule, so you are calculating the derivative back, and then each different neuron is getting a separate update. So we can talk about it offline because it's a complex thing. But here I just don't have. I omitted some information that would help me to explain to you in more detail. It's like a simplified version.
Okay.
Last chance. Anyone? Good.
Here.
2 people actually. Okay, I don't mind if we take 5 extra minutes. So if you're okay with that, we'll take both.
Yeah.
That was nice talk. Thank you very much. So about sending the updates for the neural networks, can you actually protect those updates, I mean, against sending you malicious data? Because when you send only updates, I guess you cannot really say whether those updates cannot break your coefficients or something.
Yeah. I mean, I guess that what you are trying to say is, what if someone tries to send an update that is deliberately bad?
Yeah, if
Okay.
someone's trying to break your neural network.
So in that moment, you have several things you can do, because in the federated server, what you will try to monitor is how did your model do after the update. So if you see that your model, after this update, your model is diverging or is doing very bad, so there are ways that you can handle that. And this can come from a malicious update or from a good update, because sometimes, some data might be corrupted and you don't know about it because you have millions of patients, let's say, but one patient has some artifacts because some data is missing, whatever. And it can happen. It's the task of the federated server then to monitor that the training is being done properly. I don't know how an implementation of that specifically handles that. If the iteration is just thrown away and another iteration is calculated, but it doesn't seem to be like a showstopper for this type of thing. It seems to be you have to think about that, because this can come as a product of the training that you eventually diverge. So you have to account for that. Yeah.
Okay, thank you very much.